Physics 2, Lab 2. It's Quentin Numson's presentation. All right, so brief introduction. The purpose of this lab was to create a model of two charge tapes. However, differing from Lab 1, the charge is now evenly distributed across the entire tape rather than being modeled as a point charge. This model was then used to estimate the amount of charge required to counteract the gravitational force on the bottom tape. So there's also the lab where the charge was calculated to be at 2.0685 times 10 to the 10 to the negative eighth coulombs. The electrical force was 1.47. 157 times 10 to the negative third, and the gravitational force was modeled to be about the same. So a few key physics ideas for this lab. First off, Newton's second law. Again, very important. This was simply used to calculate the gravitational force. Coulomb's law, again important, used to calculate the force between the tape. In this case, it was used to calculate the force between each individual charge, each individual dq, essentially. The important thing is equilibrium due to lack of motion. The fact the center of the tape was not being acted on by any other force when floating, the net force, or the tape as a whole, the net force must be zero. Distributed charge, this was important for calculating, this concept was important for calculating the individual charge in each point and the individual E field at each point. It's kind of dq over dl is equal to q over l. It's a very important concept to know. And also just a quick definition of the system and the surroundings. The system is defined as simply the bottom tape, while the earth and the top tape are included in the surroundings. So here's the code and measurements. So again, you have your k value and your g value. Those are given constants. The mass was calculated using the length, which was 15 centimeters, divided by 1,000, which gives the mass in kilograms. Estimated net charge on the tape. This was found using simply trial and error until the charge calculated by the computational model was equal to the gravitational force. At the very bottom is the not equation, the program, or the code used to calculate the E field. Then you can see the initialization of the top tape and the bottom tape. And in the middle of here was the code that created the two lines of tape. However, I chose not to include that as I felt it would be redundant since everybody's was the same. And again, there's the scale used for the electrical arrows, the electric field arrows, and the initialization of scale for the FE, and the initialization of the electrical force. Then at the bottom there is the code, which then calculates the force at each of the individual points, the DQs, individual charges, and then calculates creates an arrow to represent that. The bottom tape. This then models the gravitational force and the electrical force and arrows, and prints out the magnitudes of the two forces. Here are the results, as can be seen. Yes. And so a few assumptions and errors. First, we assume that air resistance is negligible. The mass of the tape is 1 gram per meter, and that the charges of the tape have about the same magnitude, evenly distributed across the tape. So we did not assume it was a point charge for this lab. A few possible errors. Touching the tape could cause uneven charge, and the charge could also be dissipated throughout the environment. So if we model this lab as a point charge, what would maybe differ? So first, lab 1, which we did model as a point charge, the charge came out to 2.0207 times 10 to the 8th, versus lab 2 was 2.0685 times 10 to the 8th. So you can see there is a clear difference there. So why do these values differ? What's causing this? They differ likely because this lab calculated the charge across the entire tape. This would result in a different distribution of R vectors at each individual point, which would result in different calculations, and that the R value was not great enough that the tape could be treated as a single point charge. This lab is also likely more accurate than lab 1, as it is far more comparable to reality. Thank you.